Thank you very much. I will just quickly recap what we did last time. We defined the expander family, and then we essentially did survey one construction that was by Margulis and others also, but essentially by Margulis, which used Gazdan's property T, and we saw how property T was used to construct an expander. And then we briefly saw some property which we called property T, and that was roughly copy or mimicking the proof that we saw last time. We just dropped the property T from the context, and the rest of the theorem, which was giving us an expander family, we kind of defined that to a property called property tau, and that will be observed that it's very useful in various fields. We will not be looking at the applications of property tau as such, but just to mention that this is a very important class of groups which are connected to various different areas. So today I will continue with two more constructions. I will give a brief outline to what little I understand about those. And to start with, I mention what is called Alon-Bopanna theorem. And we observe in the definition of expander graphs that these are graphs for which we need enough expansion. Given any subset in our graph, we want the boundary set corresponding to that subset to expand in a certain sense. So here is a quotation from Sarna, which says that we need expansion, but we also realize that there is a limit to it. We cannot have arbitrary expansion. So here we consider a graph which is k-regular with n vertices. This is essentially the adjacency matrix, and here we look at the eigenvalues, and we look at the maximum of the modulus of its eigenvalues, which are not essentially we want to avoid the highest eigenvalue to the constant function, which is the eigenvector. So essentially this gives us a measure of the gap. So k minus this would be the gap. So this Alon-Bopanna theorem in this context says that if we have a graph, k-regular graph with n vertices, if we have a family of them, then this number, the maximum of the modulus of eigenvalues, the lim-inf of this is bounded below by 2 times square root of k minus 1, where k is the degree, which can also be written in this manner. So it tells us that, for a large k-regular graph X, the upper bound would be, the maximum we can expect is is 2 times root over of k minus 1. Now, we are essentially considering families of such graphs. Now, we will call graph, finite graph X to be Ramanujan if it's if this lambda for X, the finite graph X, is actually bounded above by this number. So the maximum we can get is 2 times square root of k minus 1. So a graph is Ramanujan if it's let's call it the gap, let's call it the spectral gap. I do not know, different references talk about it differently, but most references call this to be the spectral gap, which I assume to be the right nomenclature maybe. So let's call this the spectral gap, and I will call a graph to be Ramanujan if this number is bounded above by 2 times square root of the degree minus 1. So this would be in some sense an optimal expansion in an expander. Okay, so now I will try to talk about construction, explicit construction of Ramanujan graph that was given first by Lubotsky, Phillips, and Sarnak, and this was I guess in 80s, and it was also constructed by Martin Liss independently, probably a little later, and this will also be this construction of Ramanujan graph. We will also get it through Cayley graphs of certain groups, and I will try to give a sketch of what's going on here in this construction of Ramanujan graphs. So these graphs are denoted by x, p, q. It has 2 indices, and here we take p to be a prime which is congruent in 1, 1, 4. Now we consider the integral quaternions. Here we consider the integral quaternions which look like this. Here is I square, g square, e square, these are all minus 1. And so this is the standard quaternion with integral coefficients. This is how the conjugate would look like. And this is what we call the norm of alpha. So norm of alpha is the sum of the squares of the coefficients. So now what we would essentially be trying is to get a Cayley graph with a symmetric generating set. Now here this set SP that we are looking at, it will serve as the symmetric generating set for, not exactly SP, some quotient of SP that we will be looking at in a moment, will serve as the symmetric generating set. And the cardinality of SP would be P plus 1. I will not go into the details. It involves quite a bit of calculation. The reference for this would be the book by Davidoff, Sarnak, and Ballet. So it's a book from Cambridge University Press, I think. So SP is the set of all such integral quaternions such that its norm is P. So norm is P, and alpha, the quaternion alpha, is congruent to 1 modulo 1 mod 2. So So what do I mean by 1 mod 2? I mean, we will be having these as the coefficients. So 1 mod 2 would imply that only this would remain, because if all the other coefficients are even, then all the other terms vanish. So only the constant term will remain, and the calculation which is behind this figure, that the cardinality of this set is p plus 1, that tells that there are choices. I mean, when a naught would be greater than 1, I mean, we will have these three numbers, a1, a2, a3, all to be even, and this being odd. So only this number will remain, and so since this is odd, mod 2 only 1 will remain. So alpha. So for such alphas where you have this a naught greater than 1, yes.
This is the first step little bit once more. How the SP, sorry, second step.
Yeah. So SP is the collection. These are the integral quaternions.
Yeah, that's fine.
Yeah. So these are the integral
modular thing. Can you explain?
So alpha is congruent to 1 modulo 2. So here we have these 4 coefficients, right?
Yeah.
So there is a calculation behind it which shows that there are 2 possibilities, and if a naught has to be greater than 1, then the possibilities for which we get n alpha to be p, the norm to be p, is that all the other coefficients a1, a2, a3 to be even, and in that case, and a naught being odd. So a naught being odd and all the others being even, that would imply that these terms would vanish, only this would remain, and mod 2 1 will remain. So that's what is written.
Basically, the modulo with respect to the quaternion you are defining, not because it has technically 4 coordinates.
Yeah. So I'm applying the modulo only on the coefficients, but if I take the modulo mod 2 of the coefficients, if these are 0 bars, so then I would have only this.
Okay.
So that set would have p plus 1 elements. So then, suppose I have this set. So this set would have elements like alpha bars, and so on. So if you take the pairs, because pairs would occur in this expression, right? So all of them, they would be in this, and you remember that we want a generating set, we want a symmetric generating set, and from that perspective, we will need alpha bars to be in SP. Anyway, so now we consider this integral quaternions Hz, and we consider the reduction modulo Q for another prime. Sorry, I think I have missed that choice here. That we choose a Q which is also 1 mod 4 and which is different from P. So we choose another prime number Q which is again 1 mod 4 and is different from P. For that prime Q, we consider the quotient map, the map from Hz, the integral quaternions, to Hz mod Qz. So we take elements here and we just look at them mod Q. So we consider that map, and now we will look at these elements here, mod Q elements here, as 2 by 2 matrices with Z mod QZ entries. So typically they would look like so a naught plus a naught plus a1, then a2 plus a3, something like that, and then the conjugates at 2 1 position and again at 2 2 positions. So sorry, I haven't mentioned the matrix, the explicit map. So here we consider elements of this type with mod q coefficients in the form of 2 by 2 matrices. And this can be shown, this is not too difficult, that this would be isomorphism with the norms of those elements being the determinant of the corresponding matrix. And if alpha here is a real quaternion, that means we don't have these, then the corresponding matrix would be a scalar matrix. So I mean, with these two restrictions, we can show that there is an isomorphism. So that if you write down the map and check that, then we will get the norm to be equal to the determinant, and corresponding to these type of elements, we get scalar matrices. So first, now, yes.
Take 2 primes, modulo 4, modulo 1, mod 4, modulo conjugate to 1 modulo 4.
Yes.
These are different PQ.
Yes.
There is no other restriction, only modulo 1, conjugate 1 modulo 4.
On Q, you mean?
P and Q both are the same congruent 1 modulo 4, but
yeah, they are congruent 1 modulo 4 and they are not equal. That's all. That's all. No other restriction.
Okay, this map M2, whatever this M2 of this, it is something like a Mobius transform, some that type of surface coming. Because determinant is coming.
Yeah.
It is some kind of angle preserving thing, because it is a quotient map, quotient space.
Yes.
And it is something like homogeneous space type of thing. This type of.
Yes. But I haven't thought about it.
Okay. Sorry.
No, it's a good question. I mean, it looks like, now after you asked, it looks like.
Just like a homogeneous space, you open up when considering a similar area.
Yeah, but I haven't thought about it. Sorry, I will.
I'm also really. I know it is there, but I'm not really.
Okay, maybe I'll think about it and get back to you.
Thank you.
So now what we will be trying to do is, starting from this symmetric set, we will try to construct a symmetric generating set for our group, and we will come to, I mean, what are we considering as our group, whose Koenig graph will give us a Ramanujan graph. So now what we look at is that if we take elements from SP, then you take these two maps, you compose these two maps. So from HZ you come to HZQ, and then from HZQ you come to M2 of ZQ. So it can be checked. This is also not too difficult, that this image is actually in GL2Q, and actually you can see that the determinant is norm of alpha, right? And the norm of how did we consider this set? The norm of alpha was P, right? And P is not equal to Q, so so the determinant doesn't vanish, right? So that's all. So if we consider elements from SP, then if we send them from SP, we will get an image in GL2Q. I mean, which is a subset here. And then we we see that if we are taking elements of this form alpha alpha bar type, they do map to uh, scalar matrices in GL to Q. So we will eventually get rid of these things and we'll take a quotient. So here we are taking the quotient by the scalar matrices, so that we don't have two things mapping the same element, scalar element in GLQ. So we go down to PGLQ. So now what we will be doing is we will take the image of SP under all these maps. So first we come from HZ to HZQ and then to HZQ to MZQ, and then we actually find that the image is not in image is actually in GL to Q. Now from GL to Q also we pass on to PGL to Q. And what we do is we project this SP inside PGL to Q, and that set we call SPQ. And since SP is a symmetric set, we can easily check that SPQ we obtain this way would also remain a symmetric set. So now if Q is large enough, now that large enough thing is actually greater than 2 times square root of P. That is what they mean by saying large enough. Now, if Q is greater than that value, 2 times square root P, then we can show that this set also has. I mean, we don't have any proper quotienting happening on this set. We have all the elements retained. So now that's our set. That's the set we will be considering as our symmetric generating set. And excuse me. And now we will look at two different situations. One is either if P is congruent to a perfect square modulo Q, which we denote this way, the Legendre symbol, I think it's called. So if P is congruent to a perfect square modulo Q, then this set, that calculation itself would show that this set is actually contained in PSL to Q. So we had got this set inside. We apply phi at the end, so we get it here, and we can check that if P is congruent to a perfect square modulo Q, then this set is actually containing PSL to Q instead of being contained in PGL to Q. It's contained in a smaller subset. And in that case, what we do is, since SPQ is contained there, and it generates, and we consider the Cayley graph of PSL to Q with respect to this set. Now this becomes a P plus Q regular graph, and this would be the choice of the Ramanujan graph that Lubatsky, Sarnak, Phillips they constructed. In case P is congruent to a perfect square modulo Q, and if it is not, then the Legendre symbol, that function being -1 in that case, this set will actually be contained in the complement of PSL to Q, and inside PGL to Q in the complement of PSL to Q. And in that case, we take the Cayley graph, but of PGL to Q, and we call that to be our XPQ. and that happens to be a bipartite graph. It will happen. It will be an expander, but it will be a bipartite expander graph. But the most interesting situation that they mention, I have seen a few instances where why they call it, but I don't have a very good feeling why they emphasize more on this situation. Probably because it's a non-bipartite expander graph. So in this case where it is perfect square modulo Q, we take this p plus 1 regular graph, and by the construction itself, it can be shown that the lambda, I mean the choice of Q that we made, so that the set contains p plus 1 element, and that would give that the lambda, the what they call the spectral gap, is equal to 2 square root of p. If it's a p plus 1 regular graph, so that's the maximum that we can have. So and now if we consider a graph like that, and you see, I mean, in our definition, we call something an expander family when we have a sequence of such graphs where I mean, always the spectral gap is bounded below. So here we get a graph like that, and now if we vary Q here, all the time we get the this expansion to be equal to square root p irrespective of Q. So we take this family of xpq for Q a prime, and that gives us a family, an expander family. And that's an optimally expanding expander in the sense that we have achieved this. So roughly, I mean, very briefly, putting a lot of things under the carpet, this is what I think the essence of Lubotsky-Phillips-Sarnak's construction, that you start with quaternions, you pass on to, I mean, from integer to z mod q, and then you look at it. The key thing is here that you look at them. Sorry, here that you look at the quaternions in the form of 2x2 matrices, and then with these norms and other things, you look at you observe that they are actually invertible matrices, and then you find suitable generating sets for them as well, and you look at the Cayley graph. That's essentially what the construction of Ramanujan graph says. So, any question? Okay. So the next thing I would try to talk about is something called a zigzag product. This is another typical family of expanders that whose construction is a very celebrated one, and I think it's quite it's very important for application, especially in computer science and other related areas, networking, etc. So, what I understand about this construction of this expander family, this was done by Ryan Gold, Badhan, and Wigderson. So, they constructed expanders starting from, say, expanding graphs. You start with say, one graph which is of certain type, which is a suitable one. You choose a suitable one, and then you sort of keep composing the graph with itself in a particular way that they call the zigzagging. And what you construct is a family of regular graphs which has enough expansion. So what they do is essentially you start with a nm graph where n is the number of vertices and m is the degree. So you have an n regular graph with n vertices, which is x, and you look at the numbers carefully. That we are taking m regular graphs with n vertices, and then we are taking m d graphs, which are d regular graphs with m vertices. So then we are sort of zigzagging them into something which I denote here x compose y. Most people use different notations like circle z within a circle and some other notations. So this is a little non-standard notation for this zigzag product. So what is happening here is they are trying to compose they're trying to compose two graphs of suitable degree and size, and then trying to bound the expansion in the composed graph in terms of the graphs we had started with, which are x and y. So what are they doing? So they start with a graph which may initially look like a bizarre thing, but there is a reason for this choice which will be evident right now. So they take a graph with size d to the 4 and d regular. Sorry. It is d regular and size d to the 4. Yes. So what they do is they look at the square of this, and what do they mean by square? We take the graph with the same vertex set, and we join edges for a path of length 2. We join edge between the endpoints of paths of length 2. So that's what we call the square. And here the square is of the vertex set is of the same size, and the the degree increases. The degree is squared. So what happens here is, if we start with a graph of this size and size and degree, then we get a graph with the same vertex, same size vertex set and squared degree. So that's the first step. So what we do is we start with this graph x naught, which they show it exists using some good amount of combinatorics, and then they take a square of that graph. We start with a graph of these parameters, then we take a square of that graph, and then what we do is that's the first element in the iteration. So we start with this, then we take a square, and then inductively what we do is our x2 would be x1 squared compose x naught. So x2 would be x1 squared compose, this I call compose. So x1 squared compose x naught. Now what is x1 squared? X1 is x squared. Now x squared is a d to the 4 d squared graph. Okay, so now here we consider x1 squared. Now this is x1 squared, and that is d to the 4, the vertex set remains of the same size, and this changes, right? So here it is d squared. Now when I consider x1 squared here, this becomes d to the 4. So when I consider x1 squared here, it becomes d to the 4, d to the 4. And here I have x naught, which is d to the 4d. So we are in a situation like this, n, m, and m, d. So here I have d to the 4, d to the 4, and here I have d to the 4, d. When I compose them, what I have is d to the 4 and 4, 8, and a d squared here. So this graph xn would be, xn's parameters would be d to the, so xn minus 1 would be what? Xn minus 1 would be d to the 4 times n minus 1, and the degree would still be d squared. Now if I take square of xn minus 1, the parameter would be d to the 4n minus 1 d to the 4. Then I compose it again with x, which is d to the 4 and d. Then the composition would be d to the 4n comma d squared. So this is how they are iterating the product. And this composition is giving rise to the family which has elements like I mean the graphs in this family are of increasing size, and they are all d-squared regular graphs. And it can be checked that the Chigar constant would be bounded below by d squared by 4 for all n, and hence they will form an expander family. So I found this construction very strange and amusing. It's so simple to at least to understand why why it should work, that they are multiplying the size of the vertex set in a very clever way, while keeping the regularity constant. So this is the zigzag product. Essentially, first you square and then you take this composition, and you generate a family of graphs, d-squared regular graphs whose vertex sets are increasing, and it can be showed. It's not too difficult. Modulo certain things. It's not too difficult to show that the Chigar constant there would be bounded below by d squared by 4, and yeah. So here I haven't mentioned one thing, that is the expansion in the initial graph is taken to be half. Expansion in the initial graph was taken to be half. With that, the Chigar constant looks like this. Yeah, that I have missed. This is actually, this x naught is a graph with size d to the 4 regular, d regular, and with expansion constant half. With that, the Chigar constant is bounded below by d squared by 4 for all n. And that's how it gives rise to an expander family. So yeah, these are the two constructions of expander graphs. Different expander families I wanted to outline. So any question regarding this? Okay. So I will only mention about a few different classes of few other classes of expanders that some remarkable classes. Proofs. essentially they are in the same line to the Margulis's proof using property T, but not always. Sometimes they use probabilistic techniques. There is a probabilistic characterization of expander graphs in terms of convergence of random walks, and sometimes they use those characterizations. Sometimes they use strict analytical and combinatorial methods. But mostly I found the proofs to be essentially in the same line of Margulis, but with particular intricacies depending on the classes. So here are a few examples that I listed. Now, this was a question asked by Lubotsky and Wise, that all the examples so far we have looked at are all Cayley graphs. So it seems quite a natural question to ask that whether being expander is a group property that given a sequence of Cayley graphs of a sequence of groups. Say I have a sequence of groups Gn, and I have their corresponding Cayley graphs, and suppose they are forming an expander family. Now, is it always true that if I consider any set of Cayley graphs of the same groups, maybe of fixed size, they will always form an expander? They will always form an expander family? So, if right, the answer is no. And this is one striking example of such a situation. And this is an expander family of symmetric groups, which Martin Kasabov proved. His techniques are quite difficult, I would say, and combinatorial, and he also uses a lot of algebra from the classification of finite simple groups and such things. And in this case, he constructs, in case of symmetric groups, he constructs a generating set of bounded size, a generating set for Sn of bounded size, of course for n greater than or equal to 5, so that for certain k and epsilon, this family, the family of Cayley graphs of Sn with respect to that generating set of bounded size, that's an important thing. We have to make it an expander, but there are also generating sets available of bounded size for which Sns do not form an expander family. So in that sense, Kasabov's result is quite striking, that for a group, for a sequence of symmetric groups, you can actually cook up a generating set, a symmetric generating set, for which this is satisfying the expander, the definition of an expander family. But there is another generating set for which it is not. So that is quite striking, and there are other examples like. So these are examples and non-examples. So here I mentioned the solvable group example, that it never gives an expander family. Sorry, it would be Gn. So the proof is quite in the similar line to the case of amenable groups that I mentioned last time, that the same proof of Margulis's theorem the same strategy in the proof of Margulis's theorem doesn't work when we drop the property T assumption. That time I mentioned that amenable groups would not give us expander family if we carry out the same strategy. So essentially, the reason there are different proofs. So one thing one can say is that there would be almost invariant vectors. Almost invariant vectors doesn't necessarily force the representation to have an invariant vector. So the main strategy in the property T case was property T says when we have something called an almost invariant vector, so then we are forced to have an invariant vector. So if we start with representations which does not have invariant vectors, then we can say for such property T groups that we do not have almost invariant vectors. So we can hope to find epsilons for which the difference between the pi g v minus and v to be bounded below by epsilon times the size of v. So that was the main ingredient that we used to prove existence of to construct expanders. Now these groups, finite solvable groups, they are amenable groups, and we can use the same method to prove that they cannot give rise to expanders, or there are other probabilistic proofs also available for this kind of this situation, where people say that if we start a random walk on these groups, they are of increasing size. So then there is a characterization for amenable group that there will be a certain return probability, and for solvable groups, we will see that if we have to have certain return probability, we will not have enough expansion. So this type of groups will not give rise to expanders, solvable groups. Now, this is a very, kind of remarkable theorem, which says that this is also by Kasabov, Nivotsky, and Nikolov. They prove that there will be k and epsilon such that finite simple groups will form. There will be certain generating set. There will be Cayley graphs, k regular Cayley graphs, such that it will form an expander family. Their proof was except for this class, and these are Lie type groups. So they proved with different methods. Their proof didn't consider this case. It was later proved by Bria, Green, and Tao. They have generalized this proof to other more broad situations, approximate groups, and so on. So there is this last situation, which is the Bourget-Gambour theorem, which essentially talks about something we mentioned in the last class, last talk. That in that talk I mentioned that is Ln. So we will be having concurrent subgroups, and using concurrent subgroups, we will be able to form expander families in SLNZ. So if you remember, what was used there was essentially the proof. The property that SLNZs for n greater than or equal to 3, they have property T. So property T of SLNZ was used to show that the congruent subgroups there they will give rise to expander families. And if you remember, I mentioned the n equal to 2 case, where in SL2Z, there was a difficulty because those groups are not property T, but there was something else called Selberg's 3 over 16 theorem, using which we didn't prove it. We mentioned that there is enough expansion, that the spectral gap is bounded below. So that essentially proved that there is an expander family of quotients, similar groups, by congruent subgroups, the triad graphs with congruent subgroups in SL2Z, which forms an expander family. But this was a long time question which people were thinking about, that whether there is any intrinsic method of proving existence of an expander family in such groups without taking resort either to property T or to Selberg's theorem. If there is any direct method. So after a long time, so this result by Burger and Gambut, they proved that for k greater than equal to 1 and tau greater than equal to 0, I mean, they will greater than 0, they will have enough some expansion coefficient such that the Cayley graphs in such cases in this SL2P, I mean SL2 Z mod PZ, with respect to generating set of size 2k will form an expander. So their proof uses the girth, which is the smallest, which is the size of the smallest cycle in these graphs. So there is another characterization in terms of expanders, I mean, of expansion in terms of girth. So they showed they use that characterization of expander graphs to prove directly without taking help of property T or Selberg property that these groups will form an expander family. So these are a few examples that I found interesting, and in applications, so my interest in these graphs, expander graphs, they stem from something called property A, which talks about coarse embedding of Cayley graphs of groups inside Hilbert space. I mean, that means uniform embedding. If we are able to embed Cayley graphs uniformly in a suitable sense inside Hilbert space, then we call that to have property A. It has equivalent characterization, different equivalent characterizations. So I was interested in such groups which have property A, and property A is also closely connected to something called Hagerup property or atunability, which is a very nice, interesting properties in such groups and representation theory. So I was interested in such questions. There I found that the counterexample that exists, all of them, they are using expander graphs in order to construct counterexamples, in a sense that they are constructing Cayley graphs so that larger and larger sized graphs are embedded inside the Cayley graph, so that in the limit, so the construction of such groups were done inductively by taking quotients inductively, infinite quotients, and at each stage in the Cayley graph, the proofs were embedding a certain expanded, graphs in the family of an expander. So suppose I am constructing Cayley graphs, I call it gamma n, and in gamma n there would be theta n embedded, where theta n, the collection theta n, forms, so there would be theta n inside gamma n, such, and gamma n I construct, say, from gamma n minus 1, I somehow take a quotient and construct gamma n. And in gamma n minus 1, I somehow embed a theta n minus 1, and in gamma n, I embed a theta n, sorry, a theta n. And this way it goes on. And this family gives an expander. Now, why do they talk about such things? Because there is a property of expanders that they do not coarsely embed in Hilbert spaces. So the expansion in such graphs are not compatible with the Hilbert space metric. So they do not coarsely or uniformly embed in Hilbert spaces, and that is the property in such groups. Suppose I am constructing such sequence of sequence of quotients of groups. So in the limit, if I get a group, say gamma, which is in some sense the limit of such groups, then that group, the Cayley graph, would contain this family in some sense. We can find these theta n's embedded in the Cayley graphs, in the Cayley graph, and that would make the Cayley graph unembeddable in Hilbert spaces. And that was very important because if you cannot embed your Cayley graph in a Hilbert space, that would give that would violate something, and that would say that my group is not satisfying certain properties, and so on. So that was, till date, maybe only a little variance of such constructions are the only available constructions for such counterexamples. Essentially they are very similar. They are a little different, but they are very similar, the constructions. And all of them, they essentially involve expanders or something, some weak form of expanders to be contained in the Cayley graphs. So that was the main reason I was interested in expanders. And these constructions are also quite remarkable. This was by Gromov, and in constructing such groups, such family of groups, such quotients, he used something called he introduced a model called random groups. He was taking quotient of a group with a randomly chosen set of relators, and in that random quotient, he established existence of these expander family embedded inside the key and so on. So that was quite remarkable and very difficult. Some 3 sets of explanatory notes were written about this construction of Gromov. So it's still quite obscure. And other applications I saw, found very interesting was application of Ramanujan graph by Helene Ballet to see some different classes of norms on certain C-star algebras, and also proof of the fact that certain kind of elements are generic elements in something called a mapping class group. So in all these things, I have seen expander graphs being used. I don't know the intrinsic graph theory aspect of expander graphs, the spectral graph theory aspects much, but the applications I have seen, especially the first 2, they are very remarkable, and I mean, expander graphs play a very important role there. So yeah, that's how I I see expander graphs. So thank you. I don't know whether these could clear any anything for you, but yeah, I tried to say what I understood. Thank you very much.
Thank you, Subrata. Yeah, it was a fantastic talk. We all enjoyed your talk. Yeah.
Thank you.
Yeah.
Thank you very much.
Audience, if you have any question, we can ask.
Your references are the same last time what you have said.
Last time I mentioned that geometry group theory. Yeah, that reference is also here, but there are other references like the paper by Reingold, Badan, and Peterson, Annals of Mathematics paper, and also their survey note on bulletin of AMS.
In the slides, you can mention those things.
Maybe I will update and I will send the slides to Rajesh.
The references will be.
Yeah, I will add the references and send it to Rajesh. Sorry, I forgot to mention the references in the slides. Any other question or comment?
Any recent development in the construction of the expanders?
So these results by Green and Tao, they are fairly recent, and results by Kasabov also is not very old. I mean, any other strikingly different method of constructing expanders, I am not aware of. But I can mention one result by Damian Usaida. It is very much in the same line as these constructions by Grumov, and there he constructed a weaker version of expanders, and he constructed by hand a family which is like you can call it a weak expander, and it was of course done with certain purpose in mind, but the construction was quite involved and very nice. It uses Lover's local lemma, I think, if I can recall it correctly. It uses that Lover's local lemma very, very strongly, and the construction is very combinatorial. It was done with certain purpose in mind, but I think in itself the construction of such graphs was very, very remarkable.
Thank you.
Are there other questions? Okay, if not, let us thank Subhabrata for this interesting talk. Thank you, Subhabrata.
Thank you, Rajesh, for calling me.
Thank you so much. Yeah.